Alright, well, today I will be demonstrating how to work with Comsol Multiphysics 6.3. What I will be doing in today's demonstration is I will illustrate to you how to sort of simulate a cantilever beam in Comsol Multiphysics. So a cantilever beam, for all illustration purposes, looks somewhat like that. Yeah, it's a cuboid. Essentially, it's a cuboid which has one of its ends fixed. So you could somewhat imagine that this face of the cantilever beam is fixed, right? While the other end of the cantilever beam, consequently, is free to move in space. That is, it can oscillate up and down in the z axis, and that is going to cause a few things. That is going to give you some displacement for the beam, that is going to cause some stress. So we're going to explore all of this within the Comsol Multiphysics window. And for this, we will be using something called as a static study, that since we're not varying anything with time, we are essentially going to take snapshots of different configurations, and we're going to study stress and displacement for this cantilever beam. I will just get right to it. When you just open the window for Comsol Multiphysics, you happen to see two different icons. Now, the model wizard icon helps you navigate through a plethora of options from which you can sort of initially configure your environment. The blank model is going to give you a blank model. You can still choose between the both of them, but I would always recommend to go with the model wizard if you're just starting out with this application. Since we are going to illustrate our cantilever beam in 3D, I'm going to select the 3D for space dimension. And now this is what is important. Previously, I've told you something about choosing static study, right? But the physics which we are going to be using, all of these properties which we are going to study today, come under the linear elastic properties, right? For any given material. Now, these properties are usually studied under solid mechanics. So we will be choosing solid mechanics as our physics. Now, as far as I'm concerned, I think there was a study dedicated for cantilever beams, but I think for the purpose of this demonstration, a structural mechanics, solid mechanics solid is more than sufficient. So I'm going to add that as my physics. And what I'm going to add in the study, as I've already told you, is we are going to choose a static study, right? I will go to studies. I'm going to click static or stationary study. I'm going to double click on it to select it. And now this is going to open a window with all the physics and all the studies pre-equipped in it. Yeah, you gotta let it take a moment. Now, if this is the window you see right after you've made your initial set of selections. You see the first geometry window where you have to make sure that your units are in meters, since we are demonstrating a macro cantilever beam. And once you have made sure of that, you can go to this icon called geometry, and there's a whole lot of options here. I want you to put your focus to primitives. There's a lot of different fundamental 3D primitive shapes you can choose out of, but since our cantilever beam is mostly cuboidal, we will be going with the block. You can see, if I show you the dimensions of this at the moment, you see we have somewhat chosen a 1 meter length, and the cross section is simply 0.1, so that 0.1 surface is extruded to a meter, which is what we will try to do over here. Is my depth is going to be 0.1 and my height is going to be 0.1, and I'm going to have a width of 1 meter length. Let's try building it entirely, and you see that's a cantilever block. Now, as soon as you have created the block itself, you see there's a block added to my geometry. What I want to do from this point is I want to add the material to the block, right? And for this demonstration, we will be adding, and to add materials, by the way, you go to the materials window, you click on add material twice, and you can type structural steel. We will be using structural steel to illustrate our cantilever beam, and you have to give it a second. You see a structural steel option here. I'm going to double click on to add the structural steel. Now, if you notice structural steel, you sort of come to certain conclusions about its property. You see that the Young's modulus is around 200, it's around 200 megapascals. The density is 7850 kilograms per meter cube. You got to remember these values for calculations later on, but as it is, the material has been added, and this can be seen by how the whole block is selected in blue. You can also try to remember this one button here. I think it's really convenient because imagine you go to a very random view and then you're not able to navigate back to your window. If this ever happens, if you press on the default view button over here, it sort of goes to that default isometric view, which is really convenient whenever I use Comsol. Um, and by the way, clicking on your left mouse button helps you rotate your view, and clicking on the right button helps you pan your view. So these are interesting options. Now, getting right back to what we were doing. Once you've added that, go to this linear elastic material property. Make sure that your entire block is selected. By default, your block is selected. You don't have to worry about that, but if it's not, make sure that your block is selected in linear elastic materials. Now, what has happened is Comsol has created a block in free space which is not constrained, but you want to constrain your block, right? And the way to do that is to either right click on the solid mechanics option, and you see there's the option to fix constraint and boundary load, or if you cannot find that option, you can go to the physics window, and under the boundary you can find both the options I was talking about for fixed constraint and for boundary load. I'll be first adding the fixed constraint. One end of my cantilever beam is going to be fixed, right? I'm trying to fix one end of my cantilever beam. And when that is done, I can go to this second part of it where I'm going to add a load to one end of my cantilever beam. So essentially what I'm doing is I'm fixing one end, and the other end over here, I'm going to add a load, right? Some force, and um, the force will be a body load, and I'm going to make sure that it's a total force. I will add around 10 kg of force or 1000 newtons, and I'm going to add it in the negative z direction. So what it physically means to add a negative z direction force is to add a force down, because you see the z axis is to the top. If you're adding a negative force, the force is to the bottom, right? So I'm going to add a total force in the negative z direction, that it's to the down, and a 1000 newton or a 10 kg force, right? What we're going to do after this is you're going to mesh your entire system. And the way to do this is you go to the mesh window now, and there's an option for either free tetrahedral or swept. Now, a free tetrahedral is an unstructured mesh, and a swept is more of a structured mesh. And usually for these geometries, which are more, they have proper defined edges. They're like rectangles, cuboids. It's always good to use a structured mesh where it can fulfill. Now, let me just demonstrate how a structured mesh looks like. A structured mesh is a proper, like a cube box. But if you go for a free tetrahedral mesh, which I will also show you right now, you can see it's more of a random, tetrahedral shape, which is not always ideal. You want to use a structured mesh where you can. So for this demonstration, we will not be using a free tetrahedral. We will be going with a swept mesh, right? Um, Now, a few terminologies I want you to be aware of. Whenever we have a given block, now this whole part of my block is called the solution space. So what the mesh is doing is it's dividing this entire solution space into small blocks, right? Now, each of these blocks contains solutions, and at each of these nodes, these individual nodes, the compiler or the solver basically solves for different equations. It could be for linear elastic material properties or for other studies whenever we try to emulate it for other studies. And what it's essentially going to do in the end is it's going to integrate or consolidate all these different solutions at all these different nodes to give you one physical characteristic for this entire system, right? So that is why we have mesh, which sort of divides the solution space and helps the solver to solve through and converge at a given solution. And naturally, to do this more accurately, you want the size of this mesh to be as small as possible. We will make it around extra fine. I think it should be enough, but if it's not enough, we will make it extremely fine. For now, I've made it extra fine and I've built the mesh. We can now just click on the study option here and compute. If you cannot find that option, you can click on the study window here and compute, and you'll have to wait for a little bit. Usually it takes around 5 or 10 seconds depending on your computer, and also depending on whether what study you're doing. So usually for static studies it's really quick, and you'll see the default plot here is a one misses plot. Now previously I avoided discussion on a one misses plot, so I'll give you a very small gist on what a one misses stress is, right? So when you consider stress in a multi-axial fashion, that is, imagine you have multi-axial forces in different directions. That is going to cause stresses in a lot of different directions. But thankfully here I'm only adding a force in the negative z direction. But usually you have forces in all sort of directions. And it's really hard to pinpoint what the stress is going to be. You cannot have just one number, right? But the one misses plot or the one misses stress is going to give you just one scalar value for stresses acting in various directions. So that kind of helps you give a certain number for a certain force configuration. You don't have to worry about different axes, and it's a really convenient way of illustrating stress at a given time, and it's used very commonly. So that is your 4 cents about von Mises stress. Yeah, so you have the 3D plot right off the bat. You see the stress is concentrated where the cantilever is fixed, and the stress gradually or linearly decreases to the free point. We will do both these graphs. Now, when I am going to plot them, I want you to sort of expect how these graphs are going to look like, right? Now, for the one misses stresses graph, when I do the 2D plot, the graph from the fixed end, all right, from the fixed end to the free end, the stress graph essentially is now if you look at the displacement graph, the fixed end is obviously fixed, so it's not going to move, but the displacement is going to exponentially increase like that, right? Somewhat exponentially. It's going to be a little linear, but it's going to be slightly exponential. It's a higher order graph, right? And you see that is my displacement in the z direction, and that is simply my along arc length along the fixed point to the free point of the cantilever beam. This is for my displacement, right? But if I'm going to illustrate the same thing for the von Mises stress, it's going to look something like that. It's going to be somewhat linear, where at the fixed point it's the highest. This von Mises stress is the highest. Von Mises, and along the arc length, when you go to the free point, the von Mises stress linearly decreases, right? And we'll try to see both of these plots in just a second. And the way to sort of make these plots is to go to the results window here. After you have solved, you'll get a results window where I can select a 1D plot group. Now, when you add a 1D plot group, you see there's a 1D plot group over here. You want to add a line graph, yeah? And as soon as you add a line graph, you see there's an option to define a cut line. Now, cut line in uh, in in parts for a simulation basically is a line in the solution space. You see that's this one line in the solution space. Now, what this line is doing is wherever it cuts the solution space, it's extracting solutions out of it. Now, I want one end of my cut line. I'm going to select one end of it to basically be in the middle of my fixed point, and I want the other end of my cut line to basically traverse all the way to my free end. So right now, if you see, the cut line is basically cutting across a traverse section of my cantilever beam. So it's going to extract solutions across each point along the arc length, which is what I want to make these two different plots along the arc length, right? So this red line is going to extract solutions wherever it cuts the cantilever beam at. So when I do that, you see the default expression is solid displacement, which is what I want to explore in the beginning, and I want to make sure this is an arc length. Now, as soon as I plot this, I get somewhat of an exponential curve, right? It's a higher order curve. It's not essentially an exponent, but it's a higher order, which is exactly what we expected over here. Now, when I do, and the way to sort of convert this into a table is you can right click on this. You can do two things. First of all, you can click on the graph marker, and this gives you the the least displacement, which is 0, and the maximum displacement, which is around 1.99 or 0.2, approximately 0.2 0.2 millimeter. You can also change these units, by the way, if they're not convenient enough. You can go to the line graph, and you see there's an option to change the units to millimeter, and you can plot them, and they look a lot more cleaner right now, right? You can do that if you want to. It's around 0.2 millimeters. So that's how you find the minimum and the maximum. But if I want an entire table to sort of help you, and of course you can go across this graph to sort of get values at each point, or you can simply right click on this line graph, and there's an option to plot data into a table. When you click on that, I get data of displacement for different arc lengths, and you can conveniently choose 2 or 3 values which you can put inside your table, right? Now, after this is done, I want to do the stress part of it, right? It's always convenient to have another plot, otherwise both of them are going to overlap. So I'm going to create another 1D plot group, and here I'm going to add a line graph again, but this time, and we'll again make this, we don't have to worry about this. I don't want a solid displacement right now. I want to replace that expression. So I'm going to click on this button, and I'm going to go to solid mechanics here, and there's an option for stress, right? And I'm going to look for von Mises stress over here, or you can also search it here if you cannot find it. I double click on it, and there's von Mises stress here. I can add the description if I want to, and I have to make sure this is along the arc length. Now, if instead of defining a cut line again, I can choose the cut line which I had already defined in my previous case, and I can choose to plot. And you see it's pretty alright, but it's somewhat jagged on the edges, and you usually see this edge behavior because whenever you're looking for the stress plots, you see this beam here is basically locked in at this point, right? So since it's an infinitely rigid body here, and there's a point load with a maximum load at this specific point, your simulator kind of struggles to find solutions at the ends. So to sort of help the simulator, we can sort of cut the values at the extreme ends where the values are being jagged, and the way to do that is to click on your plot group, and there's an option for axis. You click on manual axis limit, and I'm just going to cut off the extreme ends where there is errors which we are noticing. And as soon as you do that, you see a lot more pretty plot. You see the plot is a lot more pretty than it was in the beginning. Whoops, we'll just go 0.1, 0.5 is too much. Yeah, you see the or maybe even 0.05. Yeah. Yeah, and you see the plot is a lot more linear, a lot more clean. There's no jagged lines. It has probably removed whatever distortion that was present, and you have to make sure that your mesh is proper, because if your mesh size is not good enough, you can see a lot of jagged lines. So I want to always make sure your mesh is either fine or extremely fine, because imagine your mesh is something like coarse, right? Um, okay, or maybe even like fine if not coarse, and imagine, or maybe even normal. Now when I'm going to simulate it with this mesh, let's say I'm going to go to study, and I'm going to study it again. You see there's a few irregularities you'll see in the solution. Now the solution is going to be more quicker, but your results aren't going to be as accurate as I will demonstrate to you. You see, as soon as I go to my plot group right now, the results are a lot more jagged, and they aren't good at all. I'll just remove the boundaries which we have set, and you can see they're a lot more jagged. They're very jagged lines than they were before, and you don't want these lines. So your mesh has to be good enough. The size of the mesh, try to always keep it either fine or extremely fine. We'll go extra fine. And one thing I forgot to tell you is you can go to physics as an option for global. Here, you can choose the gravity option, and that sort of adds gravity to this block. And since it's a macro cantilever, it simulates it better, right? So I'm also going to add gravity. I'm going to make my mesh extremely fine, and we will simulate again. We'll see how better the solution is going to be. It's going to take a little more longer than it took the previous time, but the solutions are going to be a lot more nicer, which is a good thing, right? I'm going to go to the plot now, and you see my solution is a lot more cleaner, but it's still a little irregular at the ends. So I'm going to again add a manual axis limit, and manual axis limit is going to be from 0.05 to 0.95, right? And when I plot for that, you see now it's a really clean line and it's almost linear. This is exactly what we want, right? And the way to find the extreme values once again is to right click on it and to add a graph marker over here in the line graph, and you get the maximum, the minimum stress values. And if you want that as a table to add a lot of different values, you can right click on the line graph again and you can copy it to a table to get this table, and you can find at key points different stress values you want to add. So I think this will be it for the first experiments demonstration. I hope you learned a little bit. For the next experiment, heads up, we will be covering eigenfrequencies, right? I will tell you what eigenfrequencies are in the next video, but for now, this is it. I hope you had a fun time. Bye bye.